Welcome back to NE 630, nuclear reactor physics. So today we'll start a new topic, which is the neutron kinetic equation and how to solve it and how to drive it and the assumption that we will use in order to drive the equation. So let's start. So we knew from last consideration that we have two types of neutrons. One is what? Neutrons. One is prompt from fission. The other one is what? Delayed. The prompt will get out in a time scale nearly 10 to the power of what? Minus 14. The energy from the fission is, if you look at the chi distribution, you'll notice that the most probable most probable is nearly 0.7 million electron volt. And if you look at the E average is around 1.95 million electron volts. The E maximum is sometimes nearly goes to few neutrons with almost 10 MeV, but very rarely. So this is the characteristics for the prompt neutrons. For delayed neutrons, we have 6 delayed neutrons groups. We group them according to what? According to the decay time lambda I. So we have 6 groups, and usually it goes from a fraction of what? A second to almost something like 80 seconds or so. 80 seconds. Okay, guys, and the energies for this, the average energy is around half MeV. So you have an average energy here of half MeV, you have average energy here of almost 2 MeV. So you expect that the delayed neutrons will have likelihood, more likelihood or less likelihood than the fast or prompt neutrons to escape from the system. Which one? Less. Why? Because they will take less time to moderate to the thermal energy, so they will spend less time in the reactor moderating, so they will have less chance to escape from the system. So we have to look for importance of the neutrons. So if you have two identical babies, exactly identical, and one is born from a fat lady and the other one is born from a slicky short lady, and they are like twins. If you saw the babies without looking to their mom, you will not be able to differentiate where they come from. So you have to look for their mom to say, oh, this come from this lady and this come from this lady. So it is exactly the same. This is a neutron. Can you differentiate between neutrons? No. So you will see this is a neutron, this is a neutron, but each one has different characteristics. So we have to give importance for those neutrons. So we will define phi plus as a function of R and E as the probability that a neutron, irrespective of what neutron, is it prompt or delayed, a neutron introduced at position R in our system and has energy E will ultimately result in fission. So what I'm writing here is just a probability that if a neutron, I do not yet define whether it is prompt or delayed, appear in your system at energy R, at position R, and energy E will ultimately induce another fission. So this is just a probability. And then we will define the relative importance, of delayed neutrons in group. We said that we have 6 groups, so let's assume that we want to define the relative importance of some neutrons in group I emitted with energy chi of E d I q. So what's q? Q is the isotope of interest. So if we are talking about uranium-235, Q represents uranium-235. If we are talking about plutonium-240, Q is plutonium-240, and so on. And chi is what? Is the density distribution function, which is this. This is the density distribution function. Chi of E as a function of E. So chi of E dE is the fraction of neutrons that is produced between at energy E, between E and E plus delta E. Yes? So this is, so chi of E is the fraction of neutrons produced at energy E from fission of the isotope Q as delayed neutron in the group I. So D is what? Stand for delayed, and I stand for what? Group I, because we have 6 groups. So this is just the fraction of neutrons, okay, or the probability that a neutron generated from fission in the isotope Q will appear in the group I of the delayed neutrons at energy E. Okay, guys? So let's look at this importance. So if we multiply this importance here, I, we call it IQ DI, the importance of the delayed neutrons coming from a fission of isotope Q and appearing at the group I. So it is delta V, which is the volume of the reactor. Then you integrate from 0 to infinity for delta E multiplied by the phi, the probability function that I just defined at R and E, multiplied by chi di of energy E Q from 0 to infinity again, and this is multiplied by nu sigma fission of energy E prime for the isotope Q, multiplied by number density of the fissile atoms Q at energy E, or actually number density should not be a function of energy, multiplied by the flux at position R and D prime. So what's this? What's this? N multiplied by sigma fission is just what? Sigma capital fission. So this is what? Sigma capital fission for the isotope Q as a function of energy E prime. If you multiply it by the flux at position R and energy E prime will give you what? Total number of fissions at energy E prime. And each fission will produce what? Nu. Yes? So this, if you integrate from 0 to infinity, this will give you the total number of fission neutrons produced everywhere in your reactors. Yes? But you have to multiply by what? To integrate over dV, so that you will integrate over the whole volume of the reactor. Because the flux here is a function of what? Of R. Yes? So this will give me the total number of neutrons. Then if I multiply it by chi, this is the fraction of those neutrons produced from the isotope Q. Yes? That will appear as delayed neutrons with energy E in the group what? In the group I. Yes? So those are, this is how many delayed neutrons in group I with energy E produced from isotope Q. Again, did you understand? How many delayed neutrons produced from isotope Q with energy E and appears at what? Group I. If you multiply this by phi plus of R and E, this will give you what? So phi of R and E is just the probability that one neutron appears at position R and energy E will induce a fission. Yes? So this will give you the total numbers. If you multiply by this and integrate over all energies, this will give you the total number of neutrons produced in your system that will induce a fission again. Okay, so we will define this as importance here for the delayed neutrons. We can also define importance for the same isotope Q, but for the prompt neutrons, not for the delayed neutrons. And this again will be exactly the same, except that chi of E here will be just for the prompt, not delayed. And this is again the same function. Then nu sigma fission of Q as the energy E multiplied by NQ multiplied by phi and R and E prime E prime. So this is exactly the same, but this is for delayed neutrons, this is for prompt neutrons. So we define two importances, one for the delayed and one for the neutron. Why we are making this? Because when we try to calculate the kinetic equation and solve the kinetic equation, we cannot treat the neutron the same. In the diffusion equation, when we have the number of neutrons n, did we have any importance for neutrons? No, we did not define any importance for neutrons. Yes? So we have to define some importance for those neutrons while we are doing this calculation. So now, the relative effective neutron yield, this is just the total number. Each one of those I and I is how many neutrons you produce from fission as delayed in group I or as prompt as prompt. So this is just numbers. The integration now we got numbers. So we can define relative effective delayed neutrons, delayed neutron yield of group I from fission of isotope or fissionable isotope Q. So the relative importance will be just defined as I DIQ multiplied by PIQ. What we did here is what? We got IQ DI is what? This is the number produced at DI, and this is the number that will do the fission, and this is the total number. If you multiply this total number by this fraction, so PI or beta I is what? Fraction of delayed neutrons in the group what? In the group I. So we define relative effective delayed neutron yield. So now this is the relative effective delayed neutron yield from in the group I from fissionable isotope Q. We define it as beta I from isotope Q multiplied by this importance I, Q, and DI. So beta I, which is the delayed neutron fraction in the group I, came from or produced from a fission of isotope Q. So this is group I delayed neutron yield from fissionable isotope Q. This is just the group I delayed neutron yield from the fissional isotope Q. When you multiply it by the importance, it will give you the relative effective delayed neutron yield. So this is the relative effective delayed neutron yield. This is just the delayed neutron yield. Okay, guys? So this is just the delayed neutron yield, but this delayed neutron yield does not take into the fact that those neutrons have importance, whether they are fast or slow. It will take slower time to reach to the thermal or faster time to reach to the thermal. It does not have anything here. So this importance of those neutrons come from this calculation I here, which we show over there. Okay, guys? So now, if we have bunch or admixture of isotopes, fissionable isotopes, so we have to do something like averaging, as we averaged before, if we have admixture. So we will define gamma I multiplied by beta I of the isotope Q average as equal to the importance for the delayed neutrons in the group I from the isotope Q multiplied by beta I for the isotope Q divided by the importance for the prompt neutrons from isotope Q multiplied by 1 minus beta IQ I equal to 1 to 6. What's this? For the isotope Q. If you sum all the relative fractions for group 1, group 2, group 3, group 4, and so on, this will give you what? Total beta for this isotope Q. Yes? So for uranium-235, we have total beta of 0.0065 coming from what? Beta is equal to what? I equal 1 to what? To 6 of beta what? Beta I. Okay, guys? So this is the total fraction, total delayed neutron fraction from isotope Q. If we have 0.0065 as the fraction from uranium-235, 1 minus 0.0065 will give me something like 99 point something, okay, coming from prompt neutrons. So I have to multiply this number by this importance, then add the importance of the delayed neutrons from group I multiplied by beta I q from I equal 1 to 6. So this is the prompt part, and this is the delayed part. So it is as if I am doing what? Averaging. Yes? Yes, guys? Okay.
Why is it gamma I? Yeah, what is gamma?
I will give it to you right now. So if you have an admixture, we'll define gamma I q as gamma I q beta I q average over beta I q. So this is the definition of gamma I. Okay? So if we assume that the delayed neutrons effectiveness, from now on, why we are doing this calculation? Why we are doing this calculation? What's the benefit of doing this? Again, to tell you that the delayed neutrons, you cannot deal with the delayed neutrons as just one neutron or bunch of neutrons that they have similar properties. You have 6 groups of delayed neutrons. Some of them will come to you earlier, some of them will come to you later. Some of them has energies higher than the average, and some of them are less than the average. So you have to treat them with some importance. Okay? Yeah.
So is it because they have a different effect on the K value of our reactor?
Yes. What we will see now, what we will discuss now, we will show you that we have prompt neutrons, we have delayed neutrons, then we have what we call other source of neutrons. I will just discuss in a minute, and I will show you that the reactor dynamics greatly affected by the time scale of the appearance or production of those neutrons in the reactor. And again, the delayed neutrons will take shorter time to thermalize to the thermal energy. Yes? Yes, they will take shorter time to thermalize, but you have to wait for them until they will be born from the womb of their mother nuclei. Yes? So it will take something like 60, 70, 80 seconds. So you have to wait 80 seconds in front of the operation room, making something like this, waiting for the neutrons to come. Okay? The other one, you will notice that the prompt neutrons, like a fast-crawling baby, is coming without even the nurse coming with those babies to you. You will come rushing from the door, pushing you around. But the other will be slacky, so you have to wait until they will come to you. Okay, guys? So now, let's see what else. So we have delayed neutrons, prompt neutrons. What else? Can somebody imagine or speculate what other source of neutrons we have in nuclear reactor? Somebody will say external neutron source. I will say yes. External neutron source. What else?
What if you have like a N2N scattering?
Yeah, this is very minute.
Photoneutrons.
Yes, photoneutrons. So we have photoneutron emission. So it's in some sense similar to the photoelectric effect. So how many of you know the photoelectric effect? All of you. So you have an electron that will knock a photon that will knock one of the drunk electrons on the last floor of the building, then it will throw it away from the top of the building and will leave the building. So this is the photoelectric effect. Yes? Or if you are lucky, you will get a bullet train for a guy who is in the second floor, and it will knock him from the window to the first floor, and then somebody else will come and replace him because he will not pay rent. So this is exactly the same. You are in the middle, you have somebody, and you will emit photons or so. So it's in some sense similar to this one. So you have decay for the radionuclide coming from the fission, and this beta decay will give you, will be accompanied by gamma ray decay. Usually the beta decay is accompanied by gamma ray decay. So if you have a gamma ray coming from the fission products, if the gamma rays is larger or harder in energy and larger than the binding energy of the last neutron that I give you in the exam, I told you what's the binding energy of the last neutron, which is you have just XA, XZ, A minus 1, then you add 1 neutron, and this will give you what? XZA. So the difference between this and this will give you the binding energy for the last neutron. Yes? If your energy of the gamma rays is higher than the binding energy for the last neutron, there is a chance that gamma ray will knock the XZA and it will produce 1 neutron. And this phenomena is called photo-neutron emission. And it is very well known in nuclear reactors. So, for example, I will give you some examples. So for deuterium 1, 2, the En, the last neutron binding energy is around 2.2 MeV. For beryllium 9, the En is around 1.7 MeV. For lithium 6, this is around 5.4 MeV. For carbon, it's around 4.9 MeV. So what happened is, if you have gamma rays coming from the fission products, usually gamma rays from fission products will come up to a maximum energy of nearly 6 MeV. And the 6 MeV is higher than any of those energies. Okay, guys? So you have a maximum of 6 MeV. You can knock one of those nuclei in the core, deuterium, beryllium, lithium, or carbon, and then you will produce neutrons. So in the reactor I used to work in some 15 years ago, we have a beryllium reflector around the core. So the beryllium will be working as what? Acting like a reflector, because it has low A number, so it is a good reflector. And also, the gamma rays coming from the core will knock the beryllium, will have energies above this threshold, and it will produce what? Neutrons from the beryllium that will get into the core. So after the first operation of the reactor, and you remove the extraneous neutron source, you no longer need this extraneous neutron source because you can depend on the photoneutron source in your core. So it will be enough to restart the reactor again without the need of extraneous neutron source. In our reactor here, our reactor is graphite, which has a little bit higher energy for the last neutron, so you need extraneous neutron source to restart the reactor again. Did you understand? So for the CANDU, the deuterium moderated reactor, D2O moderated reactor, the beta decay is much slower than the direct neutron decay from the fission products. So fission products, what's the decay time? Up to
80 seconds.
80 seconds maybe. But for the beta decay, because the beta decay will be accompanied by what? This gamma decay, which is almost 6 MeV. This process is slower than the decay for the delayed neutron in the group I. So this is decay constant, group I, decay constant. So 1 over lambda 1 over lambda for the beta decay, this is not the beta fraction. This is not the prompt neutron, the delayed neutron fraction. This is beta decay. So 1 over lambda will be much larger than what? 1 over lambda here, the inverse, yes? So if you remember a couple of lectures ago when we took just the dynamics of the nuclear reactor after 150 lifetimes, and we studied the case where we have only prompt neutrons and the case only when we have delayed neutrons, we noticed that the case where you have no delayed neutrons, only prompt, the power will go up to something like 150 times after 1,000 lifetimes, you will go up to 150 times the original power. So if you are at 1 megawatt, you will be 150 megawatt in just 1,000 lifetime, and the lifetime was on the order of what, 10 to the power of minus 4. If you multiply it by 1,000, 0.1 second, you will increase the power to what? 150 times. When we discuss the situation for the delayed neutrons, we notice that the lifetime goes from 10 to the power of minus 4 to just a fraction of a second or so. Yes, and we then said within a minute or so the power will just go to some reasonable value, something like, I do not remember, maybe 1 or 2 or double every a minute, which was okay for us. Yes, so this lifetime is proportional to, or the period of the reactor is proportional to the lambda, 1 over lambda. So the reactor control time is proportional to 1 over lambda. Yes, because the reactor control time is what? The lifetime plus the delayed time for the delayed neutron. Yes, and this what make the reactor control time relaxed a little bit in the delayed neutrons. But if we add now a third component from the photoneutrons, so the time, this is the effective time now for the photoneutron for the beta decay, which is coming, will assist the photoneutrons. This time is larger than even the delayed neutron time. So delayed neutrons, I have to wait for 60, 70 seconds. On the average, let's say 50-something seconds. But for the photoneutrons, I have to wait for 2 minutes, let's say. So in this case, what I am doing is I am relaxing and I'm doing what? I'm making the control of my reactor more stable. More what? More stable. If your criticality will be based on the 3 types of neutrons, will be based on the prompt plus the delayed plus the photoneutrons. If you are critical on the prompt, it does not matter. Prompt will get out, then will get in to the next generation, and it will be critical just on prompt, and this is a disaster. Everybody has to take an aeroplane and go to the East Coast if something like this happens. Okay? So this is a disaster. If you design a nuclear reactor just based on prompt neutrons, you better design a shield for yourself next to the reactor, so that if something happens, you will close the shield and just stay there like a bunker. So when you design, the reactor is critical on prompt plus delayed plus neutrons. So reactor is critical based on just prompt plus delayed plus photo neutron. So this is 10 to the power of what? Minus 4. This is almost 0.9 minutes, and this is couple of minutes. So if you are critical on the 3 types of neutrons, the reactor will be more controllable. Okay, guys? More controllable. So it's a favorable situation. So if you're designing a reactor, for example, and you do not care about the presence of low A material like beryllium. Beryllium is a toxic, by the way. It's a very, I think, very hard to machine. Not hard, very soft to machine and very toxic. So I remember when we were dealing with the beryllium, we have gloves and masks and stuff like this when we put the beryllium reflector in the core, and it was very delicate. It's a silverish-like metal. So, okay, guys. So after we give this introduction, now will come the beauty of finding things out like Feynman said. So we will derive the neutron kinetic equation. And the derivation of the neutron kinetic equation is very nice. So we have Ci is just the concentration of delayed neutrons precursors per centimeter cube in group I. So if you want to get the rate equation for dCi by dt, where they are coming from. So rate equation, d by dt equal to production minus losses. Where the Ci is coming from? The concentration. How many? Ci is like Ni, the number of radioisotopes that we took in the radioactivity law. N of T equal to N naught e to the power of minus lambda T. So Ci is Ni, but we just call here Ci so that we do not confuse you with N. N is the number of neutrons. So dCi by dt, where they are coming from, the production. They are produced from fission. So we should have sigma fission at a position r and time t multiplied by the flux at a position r and time t. So this is the number of fissions. If I multiply this by nu, this gives me what? Number of neutrons produced with what? At position r and temperature what? T. We are talking about one group equation, means we average over the energy. Okay, guys? And then if I multiply this by beta I, this will give me what? Number of neutrons produced from the fission at position r and at time t in group I. But each one of those neutrons is coming from one mom. So we will say that those moms are very non-healthy and they will not produce triplets or doublets or anything like this, just one neutron. So the number, if you count the number of babies, you will say, I have 10 babies, so they are produced from 10 moms. Yes? Or otherwise you say I have 10 babies produced from 5 moms. I don't know how. Or sorry, 20 moms. Each mom is half baby. So if you have something like this, you are saying that the number of babies or neutrons are the same as the number of moms, which is the delayed neutron precursors. So this is the rate of production of moms. Yes? The rate of production of delayed neutron precursors. Just count how many children you have, and this is the number of moms that you have. Yes? So minus, what's the decay of those moms? It's lambda I multiplied by what? Ci is how many of those moms will unfortunately pass away. Okay? Sorry for the example. I want to keep you awake. Although I noticed that there is a couple who are about to leave us away. Okay, guys? Did you understand this? Okay. So now, this is the equation. How many equations we have? How many? 6 equations for group 1, group 2, group 3, up to group 6. So we have 6 equations. Yes, guys? Now, let's write the diffusion equation. 1 over the velocity v d phi of r and t by dt equal to the fission source, sigma fission, of what? Of r, the flux of r and t. And I have to multiply here by what? Nu. But now, I have to do what? To differentiate that I have prompt source and a delayed source. So this is what source? This is the prompt. Then what's the delayed source? It's coming from the decay of the delayed neutrons. Yes? So each one of those nuclei will decay, yes, and will give me one delayed neutron in the group I. So those are the number of what? Number of delayed neutrons, yes, produced. Okay, guys? Then I will have what? This is the what? Source. So what's the sink? Minus sigma absorption at position R, phi of R and T, minus divergence of J. Yes? But J is negative d grad phi. So I will consider that what? I will consider that d is constant, for example. So this will give me d Laplace square phi of R and T. So this is just the leakage, this is the absorption, this is the prompt and delayed neutron. So when we wrote those last time, this is what? This is beta I multiplied by what? Sigma fission multiplied by the flux multiplied by nu. Yes? Yes, guys? If you add beta I nu sigma fission phi plus 1 minus beta I, or beta, not I, beta. So if you add it to 1 minus beta nu sigma fission blah blah blah, this will give you what? Nu sigma fission, which is the normal source that we put in the diffusion equation. Yes, guys? Did you understand? So the main assumption here in deriving the point kinetic equation, we will derive what we call point kinetic equation. Why we call this point? I need everybody to focus.
Because we're at the position R.
No. Everybody to focus.
It's one dimension.
No.
Neglecting spatial effects.
Yes. We neglect spatial effect. So we consider our reactor as a point. It does not matter the shape of the flux in the reactor. We assume that the shape of the flux does not change with time. So phi of R is what? Phi of R we have two situations. We have a reactor like this and have a big reactor like this. If you have a flux like this, let's say you remove the control rod from here, you remove it up, so you will have the flux goes like this, then like this, then with time the flux will return back to what? To the same shape. If you increase the time, for example, we'll have the same shape. So the flux function as a function of R or position X does not change. This is called neutronically tight core. If on the other way, this is the flux and you remove the control rod from here, you move it up, so flux will increase here, and it will be something like this. And this disturbance in the reactor core will not propagate to the rest of the core on a several neutron periods, neutron lifetime period, or neutron lifetimes will not propagate, and it will have the same shape. So I cannot say that the flux shape with respect to position R is the same. So this is called neutronically loose. This is neutronically tight, this is neutronically loose core. And again, the ratio for H over M. H is the height of the core, or the dimension of the core, and M is the migration what? Migration length, and this is, it's a large number. And this is you expect to be what? Small number. So small number H over M. So you expect that the migration length, H over the migration length, is a small number. The neutrons in one generation time or two generation time will fly from one place to the other. Then you will have the same shape of the flux inside the core. But if your dimension of the core is very large and your migration length is small, H over M will be a large number. In few lifetimes, few neutron lifetimes inside the core, the neutron will not be able to move from one part of the core to the other part, so that you will equilibrate the shape of the flux, and you will have the disturbances still the same. Why we are doing this? Because if we have a function like this of R and T, if our core is neutronically tight, I can say that I have a function psi of R multiplied by a function T of T, and I can separate those two functions. Yes? So the function R of psi of R will be always the same function, cosine of X. Okay? And then it will be multiplied by amplitude, which is e to the power of alpha t. So let's say that this is e to the power of alpha t multiplied by cosine bnx. This is what we got for the slab, solving the slab model. But it was a summation of this, and I told you that the first harmonic will dominate and the rest of the harmonic will decay away. Yes? So this is the first harmonic. So now I can separate the spatial part from the time part, and if you substitute here with the flux, so the flux will be a function of time. You will differentiate d by dt capital by dt, and you will get out what? Psi of r here outside. Yes, because it's no longer a function of time. So you will have psi of r here, and then you will have psi of r t of t. You will have the same for the ci. You will have ci of r multiplied by same behavior function t of t, and then you will have what? T of t and psi of r, and then psi of r and t of t. Yes, somebody will say, oh, but this is the differentiation with respect to what? With respect to space. So I cannot get rid of what? Psi of r. But you remember that what? Nabla square psi of r is equal to what? Beta square psi of r from the reactor equation. Nabla square phi plus beta square phi equal to 0. So I will put this relation, and when you remove Nabla square psi of r by b square psi of r, you can cancel psi of r from each term. So your equation is no longer dependent on what? On a space, but only is an equation solvable of what? Of time, and this is why we call it point kinetic equation, because it's no longer an equation that depends on what? on space. It is as if you take your reactor, make it like a point, and put it inside the Aladdin jar, and you will not get it out, of course. And this will be just a point, okay? Although it's not a point, but this will give you the behavior of the flux, the behavior of the power, let's say, or the flux with respect to time. And this is called point kinetic equation. If I am neutronically loose core, I cannot separate the flux function from, as a position, from the time function. And in this case, I have to solve those two equations, and those equations will be called the special kinetic equation. So you have to solve, it's very difficult to solve. You have to solve them numerically and so on. So did you understand what we will be doing now? So next time what we will do is we will assume this, we will substitute here, we will simplify those 7 equations, then we will look for analytical solution for some approximation and get a feeling of what's the dynamic of the nuclear reactor is. Okay guys? Do you have any question? Anything? Nothing? Huh? Which one? What? Cosine. This is the buckling. B sub n. X is the position X. Yeah, could be R, could be N.